Okay, what shape is this? Square, rectangle. It is or it isn't. It's not a circle. It's a rectangle. A rectangular solid. Woo! Now, I told you that we were mainly going to focus on plane geometry, and we have. Most things we do are flat, two-dimensional. But we are going to look at some volume and some solids, and this is a rectangular solid. We're going to look at three shapes and how to find the volume. Now, some people don't appreciate this, so I'm going to tell you anyway. When I learned volume, I learned that it was the length times the width times the height, or the length times the width times the depth. But it has three dimensions because it is bump, bump, bump. Okay? But what I'm going to try to do is condense all of the formulas, because there's different formulas for cubes, different formulas for rectangular solids, different formula for cylinders. I'm going to try to condense them all into one formula. Okay? And here it is. Volume is, now what's different from that than what we did with area? What's different about this formula than area? Because area was base times height, wasn't it? How did I write the b in base times height for area? Lowercase b. Because when I use an uppercase b, what I mean is the area of the base times the height. All right? The area of the base. So think of maybe the basement. Okay? Because I want you to think of this as a hotel. And I want to find out how many rooms in this hotel. So all I have to do, though, is walk around on the first floor and find out how many rooms, then look at the elevator and see how many floors. So the example that you have in your book is that there's 2 slashes here, 3 slashes here. So the first floor, I think there are 4 floors, but the first floor would look like this. There's a room, there's a room. This is the corner room. There's 2 more rooms. So how many rooms in the basement? The area of the first floor, the base. 12. Be 3 times 4. Now in this formula, this would be the 3 times the 4, right? So it's 12. How many floors in the hotel? 4 floors. So that would be the height. So the area of the base times the height, 12 times 4 is 48. Now how do you describe the rooms? How do you describe the units of measure? Square is squarea. Linear is perimeter. Cubes. So you'd say 48 cubic feet, cubic meters, cubic kilometers, cubic rooms. Okay? So this would be 48 cubic somethings. Got it? Okay. This is a rectangular solid. So you multiply the base, area of the base, by the 2 dimensions, and then multiply by the height. So what if you had something where it was the same base, it was a cubic shape, and all these were the same. This was 3, this was 3, this was 3. You call that a cube. What's the volume of this cube? Let's say that these were feet. Well, what's the area of the base? It'd be 3 times 3, right? Which would be 9. What's the height? 3. So times another 3, 27 cubic feet. Or feet with a little 3, cubed. This is normally given as the volume of a cube is side to the 3rd power. Because all the sides are the same, you just put the 3 to the 3rd. That's legitimate. I'm going to teach you both ways. The main thing I want you to do, though, is think. I want you to look at it and go, well, if I can just find the area of the base, then multiply by the height, I got all of them. Especially when you get to shapes that are cylindrical. We were just looking out the window at a silo, weren't we? That would be a cylinder. What would be the volume of that silo? Well, what shape is the bottom? It's a circle. So when you do the volume is the area of the base times the height, this is going to be pi r squared times the height, which is the formula that most people use. But if you just think of it, I like to think of it as a can of pineapple. Have you ever had sliced pineapples? And so you think of the pineapples going all the way up. So in this particular example, let's say that the radius of one pineapple is 2 inches. How many cubic inches of pineapple do we have? Well, if this each are inches, 1, 2, 3, 4, 5, 6, 7, well, that's 8. So this is 8 inches. This is 2 inches. So we do pi r squared. So we do pi times 2 squared. That'd be the area of the base, which would be 4 pi or 12.56. And then we'd multiply it by the height, which would be 8. Can I do that in my head? Not quickly, but we can estimate. It's about 100. 8 times 12.5 would be 100, so it's a little over 100, right? 100 cubic inches of pineapple. Doesn't that sound good? Okay. Okay, so there's our formula. Let me just do a couple more examples. The ones are in the book. Find the volume of the cylinder. It's 21 inches. And without my glasses, I'm going to say that that's, there it is, 9. So they have this one is 9, and this one is 21. So now we do pi r squared. R squared would be 9 squared. So it would be 36 pi times what? 21. I mean, does this make sense? Do you like this? If you think of it as just the area of the base, find out the first floor, and then how many floors, you can do any shape. In fact, you can do pie shapes. You can do, there's a place in Atlanta called Peachtree Plaza that has an external elevator. It's a circular elevator on the side of a circular tower. Okay? And if you wanted to find the area of that, you just have to add the area of the base and then find the area of this, add on to it, and then multiply how many floors. You don't have to think of tricky formulas. Just think, what's the area of the base, how many floors? Got that? Okay. Okay. I had difficulty drawing this shape in the little intermission. What shape does that look like, though? Pyramid. Okay, now here's a smaller one that I created out of paper. This is the pyramid. Now, most of the pyramids we're going to be working with have a square base, but sometimes they have triangle bases. Okay, but the ones that we're mostly looking at have a square base. So how many sides do they have? 5. They have the base, and then they have how many pieces coming up? 4. And we call those the face. That's the F. Okay? It's got 4 faces if it's got 4 sides to the base. If it's got a triangle base, it'll only have 3. The key point for finding the volume is the height again, except we don't call it the height if it's in a pyramid. We call it the altitude. Altitude. This would be the B for what? Base, very good. F is face. You know what? This is going to be hard. This little line here comes down. It's perpendicular. It would run right up the side. It's perpendicular, but it's at an angle. So we call it the height at a slant. It's called the slant height. You probably would never have guessed that if we'd have played hangman, but that's what it is, the slant height. When would you need to know the slant height? It's not in this lesson, but if we're going to find surface area, you're going to need to find the area of this triangle. And to find the area of a triangle, you're going to need the length of the base times the height times the 4 faces, right? Then you're going to add it to the base. But you don't need the slant height when you're finding volume. And this lesson is dealing with volume. You need the vertex. By the way, that's the V, the vertex. You need the area of the base times the height or the altitude times what? Now this is only for cones and pyramids. It's the same formula we've been working. It's the area of the base times the height, which is the altitude, times, close. 1/3. And I have seen it proven in calculus why that's so, but it's a very complex proof even for calculus, so I won't bore you with it here. But there's a reason, but it's 1/3. And for a cone, it's also the area of the base times the height times 1/3. Okay? So let's just do a little problem. I'm going to do the first one as an example in the book. 3 is the altitude, 3 inches. The base is 5 inches by 5 inches. How would you find the volume of this? Well, it's 1/3 area of the base times the height. What's the area of the base? If it's 5 inches by 5 inches? 25 square inches times 1/3. What's the height? 3 inches. Multiply those together. Is that easy to multiply? Very easy, because you take 1/3 of 3 and that's 1, so that gets rid of it. So your answer is 25 what? Inches cubed. Very good. Inches cubed. I thought you were going to say square for a second. Your mouth was starting to move that direction. Very good. Cubes. Okay. Let's try another one. What if you're going to find the volume of a cone? You know, ice cream cone? What's the area of the base going to be? What formula would you use to find the area of a base? Why pi r squared? Because it's a circle. The last one was a square, so we just multiplied length times width. But this would be, you have to find the radius. So in this particular example, the radius is 7. Let's make it 7 centimeters. The height is 8. The height would be right here. Make that 8 centimeters. So we do pi r squared. That's the area of the base. Times the height. That would be 8. Times 1/3, right? Because for pyramids and cones, it's 1/3. So pi r squared, this would be 7 squared is 49, 49 pi. I can't do that one in my head, but that would be 8 times 49 times 1/3 times 3.14, and your answer is approximately 410.29 cubic centimeters. Centimeters cubed. Aren't you glad we have the book? I don't have to do that in my head. Okay. Okay, what about a piece of cheese? At least that's what I think. When I look at this piece, there you go. What does this need to be a piece of cheese? Holes. Can't you just see Mickey Mouse running out of a little hole in the side of the thing or something, or Minnie Mouse or Mighty Mouse or something? You've got to have some holes for your Swiss cheese. Anyway, how would you find, first of all, what is this called?
Prism.
Whew, you're awesome. Prism. What kind of prism? Okay. We do have different kinds of prisms, but we're just going to call it a prism. And to find the volume of a prism, how do you think you'd find the volume of this prism? Based on what I've been telling you, what would you think? Base, area of the base times the height. That's it. You don't have to do 1/3 because it doesn't come to a peak. It's just the way it is. Okay? So what you have is, you could think of it this way. How about this? 1 big 3. I don't know. Fraction. Okay, so what we have is the area of the base is what shape? This would be a triangle, and we'd have to find the perpendicular of the height times the base, and then we'd multiply it by the height. Okay? That's it. So the example in the book has, this is 7 inches, and this is 9 inches, and this is 4 inches. Ooh, kind of clever, isn't it? So how do you find the volume of this baby? What's the area of the base? Okay, it would be 4. And if that's 4, that would be 4. So it would be 4 times 7 times what? A half. So 4 times 7 is 28. Cut it in half. Your area of your base is 14 square inches, right? Inches squared. What's the height? 9 inches. We can do this one in our heads. What's 9 times 10? 90. 9 times 4? 36. What's 36 plus 90? 126 inches cubed, because they're cubes. Cubes of cheese. You're at a party, you know, little cubes with little toothpicks sticking out of them. Okay, 126 cubic. Okay, last one. And I can't explain where this comes from, but it's the volume of a sphere, a ball. Here's the formula. 4/3 pi r cubed. So if the radius is, well, let's see what it says there. 3. Radius is 3 meters. That's a big sphere, right? How many cubic meters inside? Figure it out. Go. Those of you at home, turn the thing off, work it out. Done. I did it all down to here, then I just got the answer out of the book. Okay, here's how you do it. You've got 4/3 times pi times the radius cubed. Radius is 3. 3 cubed is 27 times 4/3. Well, when you multiply by 4/3, you divide the 3 into the 12. The 27 is 9 times the 4 is 36 times pi. So I knew 36 times 3, 108. So this is a little bit more than that. And the book says 113.04. Pretty close. Oftentimes, if you can just get the 36 pi, I'm happy, because then you multiply it out with your little calculator and stuff. I don't like to use calculators, by the way, too much at this level, because I'm not giving you a million-digit problem. I'm just giving you enough to learn the concepts. But if you want to use your calculator once in a while to check your answers, fine. But don't start depending on it, because guess what? Your brain will begin to atrophy. You know what that means? I met a young man one time who was a National Merit Scholar contestant. Okay? He was a smart kid. But because he used the calculator all the time, he couldn't do multiplication in his head. He couldn't even do addition in his head, because he became dependent on that machine and he didn't have to think himself. I've asked lots of people. I do a lot of traveling, and I'll sit next to people. They might be an accountant, engineer, corporate, whatever, and I'll say, what do you think? Should we give everybody a calculator or master their basics? And everybody has always said master their basics. Okay? So there's your free sermon. And why we don't use too many calculators. But for using them by pi, I wouldn't mind that, because pi, you get a more accurate answer. All right? Now, a couple weeks ago, I painted this room. I did. John and I both did it together. So how did I figure out how much paint I needed? Did I want to know the volume of the room? How about the perimeter of the floorboards? What did I need to learn? Ooh, that's a big word. I needed to learn all the area of how many walls?
3.5.
Well, this wall was painted too, believe it or not. Okay? Yeah, but don't worry about the door, because you have extra. So you have to figure out the 4 walls. What if I was going to paint the ceiling and the floor? I'd have to do 4 walls plus the ceiling plus the floor. How many sides would that be? How many flat areas, flat surfaces? 6, right? And here's how I'm going to show you. This is this room in a microcosm. You think it looks like a cross, right? Let's pretend that this is the floor right here, and we have 1, 2, 3, 4 walls. But then the 4 walls, this one comes in and makes the ceiling, and so now I have the what? I have the complete surface area of this rectangular solid, don't I? Now we know how to find the volume, area of the base times the height. But the surface area is you have to find the surface area of each of these 4 things. Okay? 4 walls plus the ceiling and the floor. Got that? Okay. So let's do this problem. We got in the table. It's 2 by 5 by 3. So if you got 2 by 5 by 3, and so here's your shapes. So here would be your, we'll call it the ceiling, kind of hiding underneath over in here. There's the floor in here, right? Would they be the same? Yeah, so all you have to really do is find the ceiling or the floor and then double it. How about this side over here? If this is 2 and this is 5 and this is 3, just this wall right here, how much would this be? 5 by 3, 15. Would the other side be 15 as well? Yes. So we really have to just do, okay, 2 times 5 would be the floor. And then we do 2 of those, right? And then we've got 3 times 5. And then we've got 2 of those. And then we've got this, which is 2 by, how high is that? Because if that's 3 high, this is 3 high, this is 3 high, so it'd be 2 times 3. It'd be 2 times 3 and have 2 of those. So you've got 10 times 2 is 20. 15 times 2 is 30. 6 times 2 is 12. You add them up, 62 what? If this is all meters, square meters, because area, square. Okay, 62 square meters. Okay, got that? Okay, have you ever seen what a pyramid would look like if we flatten it out? Now we made this cool little pyramid, right? What's it look like when I open it up? Okay, I've got 1, 2, 3, 4 triangular faces, which I need the slant height times the base to find the area of 1, and then multiply it by 1, 2, 3, 4, right? And then I have a real simple square, okay? So let's use some dimensions from example number 2. And these pyramids are hard to draw. Let's try it anyway. Chung, chung. Oh, that wasn't too bad. Okay, so if this is slant height 6, this is 5, this is 5. Tell me the surface area of this pyramid. Go ahead, figure it out. Those of you at home, boom, turn off your machine for a minute, figure it out, we'll come back and I'll solve it. Go ahead. Well, let me do it. 5 times 6, because it's the base times the height times a half, right? So that would be 30, cut in half, 15. And how many of those babies do I have? 4. So 15 times 4 is 60. And then 5 times 5 for the base, 5 times 5 is 25, 85. 85 what? Square whatevers. Good job. Okay. This next one I did not draw, but I think you could probably figure it out. Tell me where you would use this. What did we have in this can, this cylinder, the last time we visited him? Pineapple. Now, in Algebra 2, we're going to do this because if you were a pineapple manufacturer, wouldn't you want to figure out the most economical can for the least amount of tin? Would you? Or plastic, whatever you make your cans out of, you'd want to figure out which can dimensions could I use. A big round one that's only an inch high? Or one that's this, a little bitty thing that's this high? There is a maximum. That's where you use maxima and minima in Algebra 2 to find out what's the ideal can dimension. Now, there's more things than just economical use of metal. There's also what looks pleasing, right? And what is attractive and what feels good and all that. But besides the aesthetics, how would you find how much tin in a can? If you took apart this can, what would it look like if it was flat? If you took this metal, this all round now with the top and the bottom, and you were to flatten it out, what would it look like? So draw me a picture. Good job, good job. Mine's kind of poor, but it'd be fun to try that. It'd be fun to cut yours out and see what kind of shape comes out of it. You might have to tweak it a little bit to make it work right. But what you're going to have is you're going to have a top and a bottom, which are circles, right? And then you're going to have this, which is going to be pi times your diameter. So it's going to be bigger, isn't it? It's going to open up. So then you're going to roll this around, put one on the bottom, one on the top, and you got it. So give me a formula now. I mean, let's say that this radius is, let's do the one that's in the book just to be safe. Radius is 3, height is 10. This is 10, this is 3. So if this is 10 from here to here, how far from here to here? It would be the distance all the way around. We're just working on the big flat piece now that makes the tube, right? So this would be 10 inches high, but the circumference would tell us what that is. And the circumference is 2 times pi times r, which in this case is 3. So it'd be 6 pi, and 6 times 3.14, 19. I'm going to just estimate. It's like 18.84, something like that. Anyway. So let's just say around 19, so 19 times 10, and then we'd have to find pi r squared. So r squared would be 3 squared would be 9 times pi for this, 9 plus pi for this. Got that? And then you'd find this, and you'd find this, and you'd find this big rectangle, and you add them up, and you got it. That'd be your surface area of a cylinder. You want to make pineapples? Want to work for Dole? I don't know who else makes pineapples, but... Okay. How about this shape? What's this one look like? This is a cube, yes. So you'd only have to find, if all the sides are the same, you'd only have to find the area of one side and multiply it by 6. Very good. What does this shape look like? This is a triangular based pyramid, right? So you still have the faces, but you've only got 3 faces in the bore. And if it's equilateral all the way around, you maybe just multiply it by 4. To me, it looks like some kind of a, you know, ninja thing or something. Better stop this lesson. This subject we need because we're going to be studying in a couple lessons Pythagorean theorem, which is using squares and square roots. But this is a tool that we're going to need to be able to do tougher problems than the easy ones. That doesn't sound too straight. Tougher problems than the easy ones. Okay, we're going to start talking about radicals. Now, what is a radical? Well, the radical symbol is like this. Remember this? Square roots. So if I take the square root of 9, for example, what is the square root of 9? 3. What the symbol means is what times what will give us a 9. And unless we ask you for it, we're going to want a positive 3, not a positive and a negative. We're just going to say positive 3. All right? So what would be the square root of 16? 4. Very good, 4. Or what times itself will give you 16, 4. Square root of 25? Square root of 4? 2, right? Now, these are the biggies that you're going to memorize. I mean, you ought to have all the squares memorized. You should be able to say, what's 1 squared? 1, 2 squared, 4, 3 squared, 9, 4 squared. Okay, you get it? All the way up to at least 9 squares, 10 squares. Okay, the more you know, the better. You're going to need this for simplifying radicals. Now, radicals have properties. But before I introduce those properties, I want to make sure you understand one sentence. Here's what it is. And if you've been using Math-U-See, you've heard this over and over for years and different levels. To compare or combine, you must be the same kind. Duh. Doesn't really rhyme, but it's close. To compare means greater than, less than. To combine means add or subtract. But to add or subtract something, or to compare it, you have to be the same kind. Let me give you an example. What's 3 hundredths plus 4 hundredths? 7 hundredths. This is not hard. 7 hundredths. I'll tell you when they get tricky, okay? What's 3 tens plus 2 tens? 5 tens. Okay. What's 3 apples plus 2 apples?
5 apples.
Okay. What's 3 apples plus 2 peaches?
3 apples and 2 peaches.
That's exactly right. You can't combine them because they're not the same kind. Okay. What's 3x plus 1x? 4x. What's 3x plus 2y? 3x plus 2y. You can't combine them, all right? We use this with fractions too. What's 1/2 plus 1/2?
1.
Was 2 halves or 1. What's 1/2 plus 1/11? Well, unless you make them the same denominator and then thus making them the same kind, you can't add them or subtract them or compare them. Got it? Okay. Radicals sometimes don't come out even. What's this? What's the square root of 3? The square root of 3. Now, think of it maybe like pi, because we know that pi has a value, doesn't it? It's 3.14, da, 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 da. But sometimes we'll say this, 2 pi plus 3 pi is equal to 5 pi, right? So what's the square root of 3 plus 2 times the square root of 3? This is a little tricky now, because this is really kind of like 1 square root of 3, right? So you can think of it like, well, 1 pi plus 2 pi would be 3 pi. 1 times the square root of 3 plus 2 times the square root of 3 is 3 square root of 3. Okay? If they're the same kind, then you can add the numbers that go with them. Okay? Now, the thing is, though, the square root of 3 does have a value. If you were to put 3 in your calculator, hit the square root button or the radical button, you're going to get 1.7, something like that, I think, right? And there's a square root of 2 and a square root of 5. They have a value, but they can also be just left by themselves, and then think of this as an entity, okay? So let me give you a couple problems and see what you can do with it. What is 6 times the square root of 5 minus 2 times the square root of 5? Are they the same kind? Yes. Can you subtract? Yes. 4 square root of 5. Okay. What if we have 6 times the square root of 3 plus 2 times the square root of 5? That's it. This is as far as you go. Because to compare them or combine them, they have to be the same kind. They're not the same kind. They're different. Okay. So we just leave them alone. Now I'm going to try to follow the book closely here so I can make sense of it for you. So if you're adding or subtracting, they need to be the same kind, or just leave them alone. Just like if you had 3x minus 2y, what's the answer? 3x minus 2y. Okay, you know this from algebra. Okay, how about multiplying them? Square root of 7 times the square root of 6. Can you multiply them? Yep. The answer is the square root of 42. Leave it alone, okay? But I want you to now focus on the number aspect of it. What's the square root of 4? 2. What's the square root of 9? So the square root of 7 and the square root of 6 are going to be between them, aren't they? Turns out that this one's going to be, I think I have it in the book. Anyway, this is 2 point something something. This is times 2 point something 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 like that. So you're going to end up with 5 or 6 for your answer. Okay? How about the square root of 42? What's that in between? What's the closest squares to the square root of 42? Well, what's the square root of 36? 6. What's the square root of 49? 7. So the answer should be between 6 and 7, correct? And it turns out that that's what we predicted, because 2 point something times 2 point something is about 6 something. Okay? So you can go back and forth. You can treat them as values with your calculator, but they're estimated values because these don't have, they're not like 5/8 you can reduce it to exactly 0.625. This is 2 point da 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 times 2 point da 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 da, okay? Only the perfect squares come out whole numbers. Okay. Let's try another one. A little tougher. 2 times the square root of 3 times 4 times the square root of 5. Go ahead, help me. What do you think you do in this one? Okay, let's multiply the 2 times the 4, and that would give us 8. Then what? The square root of 3 times the square root of 5, because they're the same kind. Numbers times numbers, radicals times radicals, and you get square root of 15. All set. Okay? Okay, how about this one? This is a little trickier, and you got to think in terms of multiplication. Here's a clue. What's 12 divided by 4? Because 3 times 4 will give you 12, right? Okay, so what times the square root of 3 will give you the square root of 21? Okay, I got two answers now. I got 7 and I got the square root of 7. Which one is it?
Square root of 7.
Because if you just took 7 times the square root of 3, it would be 7 times the square root of 3. If you take the square root of 7, radical times radical, then you get radical. But if you have number times radical, you get number times radical. But thanks for giving me both options. Okay? How many times have I said K now? Is that 19 times? You just missed one. Oh, no, I'm sorry. Okay. K. K, 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 K. Now we want to simplify them. And think about simplifying fractions. Square root of 12. Think of it like 6/8. Could you reduce 6/8 to a smaller fraction? You could divide the 6 and the 8 both by a 2. You're looking for a common factor. How do you simplify radicals? I'm going to say it in one sentence, and if you get this sentence, this is a piece of cake lesson. The only way a radical, because you're either a number or you're a radical. That's all you are. You're either, I know I can think of all these puns in my head right now about radicals and squares, right? And the squares are me, and the radicals, okay, get the idea? You're either a radical or you're a number. But the only way you change from being a radical to a number is by being a perfect square. The only way. For example, I could make this the square root of 6 times the square root of 2, couldn't I? So what? They're both radicals. I haven't simplified anything. But I could also do this. Why did I do that? Because once I've got a perfect square as a factor, these are just nothing. I could do square root of 12 times square root of 1 times, you know, I can go on all day. That won't do anything. I'm looking for a factor that is a perfect square. Now that, you just made that up. That just went through a transformation. Now that's a whole number times the square root of 3. And so this is the same as this. This has been simplified. You might say it's been reduced. And the radical is much smaller, but the only way you can take anything out and make it smaller is if it's a perfect square. This does nothing. This is the key. Let's do a couple of these. Maybe you can try one. Square root of 18. What are the factors of 18? Okay, I could do 1 times 18. What else? 2 times 9, 3 times 6. Lots of factors, right? Are any of those factors perfect squares? Which one? 9, okay? Because this is why you have to have these memorized. Square root of 4, square root of 9, square root of 16, square root of 25, square root of 36. These are the keys. So you say, are there any? Yes, I could make this the square root of 9 times the square root of 2, because that's the same thing, right? But this goes, who wants to make the noise? Very good, very good. It's kind of like a turkey with a headache or something. So you got 3 times the square root of 2 is 18. Got it? But you can't make that noise if it's not a perfect square. Okay. Goodness, we ran out. I'm going to give you another example. Here, you do this one. Simplify that one. Are any of these factors of that?
It would be 5 times the square root of 25.
Okay, let's make this one of the factors.
Wait, I did it wrong. 5 times square root.
Okay, now this is good. I want to use you as an illustration, if you don't mind. You try to do too much in your head. Most guys that I know that are good in math, even though we can do lots of stuff in our head, I'm going to put myself in that boat. I can add fast, I can multiply fast and all that. When I'm doing problems like this, though, I don't assume anything. I write it down because there's too many little mistakes you can make. Square root of 25 is 5. So the answer is 5 square roots of 2. And when I'm doing long problems, I write it down. And some of you mothers and dads are going to, yes, tell them again. Because kids that are good in math sometimes try to do too much in their head and they get lazy. But all it takes is a little wrong symbol, wrong sign, and that problem is wrong. This is not hand grenades and horseshoes. Getting close is not good enough. This is math. You can get it right. So write it down so you don't make silly mistakes. Okay. Done with radicals. Now, I've got 2 things up here. You might not understand how they go together, but we first of all have a triangle. What kind of triangle is this? How do you know it's a right triangle? Square in the corner tells you that these lines are perpendicular, less 90 degrees. If you have a 90-degree angle in there, that's a right triangle. You're right about this triangle. Now, this side is called the, we had this once, a leg. And this side is called the leg because they make the letter L, correct? And the legs are what form the right angle. Now the side opposite the right angle has a unique name which we're going to try to figure out without using hangmen, but we're going to use our powers of observation. Right here we have a little countryside scene, mountains in the background, birds flying, okay? And we have a little, it's like a kettle or something hanging from a hangman's noose right there, right? So the key is, what is that blue thing right there? A pot. What kind of a pot is it? It's not a hanging pot, it's a high pot. And what's it hanging from? A noose. That's a hypotenuse. Very good. I wish you could see the looks on this audience. You're probably groaning if you're watching this as well. But this is a hypotenuse. Okay, so now that was much more creative than the rhombus, you have to admit. Okay. So what we have is, this is called the hypotenuse. These are called the legs. Now, we have a relationship that is unique. And the Pythagorean theorem, in some books that I've looked at, geometry books, that's the epiphany or something. That's the apex. Everything is geared towards learning the Pythagorean theorem. And I've seen many proofs of this. Proofs. But let me just show you with the blocks, all right? Remember the legs and the hypotenuse. So we're going to make one that has a leg of 3 and another leg of 4. And we're going to make the hypotenuse a 5. And the reason that we know that is because even if you were to just practice with these blocks, you'd find that that would be a 3, 4, 5 right triangle, okay? And that makes a little right angle in there. Let me just put it in there so we don't forget it, okay? We've got the little right angle. So the triangle is inside, it's what's bound by this. So we're going to illustrate this Pythagorean theorem. Who do you think created the Pythagorean theorem? I like to use the word created because observed. He observed the relationship between these three sides. It was Pythagoras. And we're going to show it, though, with the blocks. Now, here we have our, this will become a good friend. This is the 3, 4, 5 right triangle. You use this in roofing. You use it in carpentry, construction, because remember what we learned? That if something is true, then, and then the reverse or the converse. So if you have a 90-degree right triangle, the sides will be 3, 4, 5, or a multiple, and the converse is true. So if you have a 3, 4, 5, then you know it's a right triangle, okay? But here's how we're going to use the blocks to illustrate this, and I hope this makes an indelible impression upon you, because now we have 3 by 3, and how do we write that algebraically? 3 squared. So this would be 3 squared. Here we have 4 by 4, or 4 counted times itself 4 times, right? And this would be 4 squared. And if we were to put up here 5 by 5, this would be 5 squared. Now you might look at that and say, well, what is so unique about that? But if you were to add this up, what's 3 squared plus 4 squared? Well, you've got 9 plus 16 is 25, which is 5 squared. So it turns out the Pythagorean theorem is leg squared plus leg squared equals the hypotenuse squared. And this is how we show it. And if you were to take these 16, see if I can do this, hold my mouth just right. If you put these on top of this, you can see you could put a 3 here, you could put a 3 over there, and you'd have 1, 2, 3 left. So it turns out that 3 squared plus 4 squared is the same as 5 squared, okay? First time I taught this in a school setting, the curriculum guide that we were using then said a squared plus b squared equals c squared. Unfortunately, I would find that we would forget which one was a, which one was b, which one was c. So I prefer this. And I remember telling the students you can write in your textbooks. And that was a big thrill because normally you treat them like, I don't know, they're the Holy Grail or something. You can't write in them. But leg squared plus leg squared reminds you that it's the two sides that form the right angle. Squared equals the hypotenuse squared. All right? Okay. That is the whole Pythagorean theorem. But what's that mean? Not all problems are that easy. So we're going to work some other problems. And we're going to use the same Pythagorean theorem, but this is a very important theorem, so just memorize it. It shouldn't be too tough. So what if we had this? 6 squared plus 8 squared equals the hypotenuse squared. What would the hypotenuse be? Good opportunity if you want. Pause me and work it out. So if you work it out, you get 100, right? Now, if you have hypotenuse squared, we're not looking for the hypotenuse square. We want to know what the hypotenuse by itself is. So we have to take the square root of both sides. Square root of 8 squared would be h. Square root of 100 is 10. So the hypotenuse would be 10. So if you had a 6, 8, 10, but you know what? After a while, you'll start learning, hey, that's just 3 times 2, 4 times 2, 5 times 2, right? So it would also work this, wouldn't it? So if you use the multiples of 3, 4, 5, it's convenient. But what if it doesn't work out even? What if you have a triangle that's 6 by 7? We know it's a right triangle because it only applies with right triangles, right? So we would say, okay, solve for the hypotenuse. And you could do this with the blocks and get really close, by the way. Let's just think of it. If you were to make a square that was, 6 by 6 and make another square that was 7 by 7, you'd have 49 in here. You'd have 36 in here. What's 49 plus 36? 85. And if you were to put this in a square and see what you could come up with, what do you think you'd get close to? Well, I'm looking for perfect squares. It would be, you could use 81, and that would be 9 times 9, right? But 85 is more. So you could think of it as I'd have to cut a little sliver and put it like that. So but this helps you to, the answer is a little bit over 9, right? This helps you to estimate. But if you were to solve it, let's solve it using what we know about radicals. 6 squared plus 7 squared, leg squared, leg squared. Whoa, where'd all that come from? Equals hypotenuse squared. 36 plus 49 equals hypotenuse squared. 85 equals hypotenuse squared. Take the square root of both sides. The hypotenuse is the square root of 85. Can we simplify that? Not really. There's no perfect squares or factors, so we just leave it. And we know, though, that that's a little over 9 if we were to solve that using our calculator. Okay? That help? So don't forget, though, if you were to go outside and you measured something and it came out to, and you measured it, and you said, boy, look at this. That triangle is 9 by 12 by 15. I wonder if that's a right angle. What do you think? You think it is? How did you figure that out so quickly there? Oh, you mean like this is 3 times 3, 4 times 3, 5 times 3? So it's a 3, 4, 5 again. That's how I did it that fast in my head. But you could work it out. You could say 9 squared plus 12 squared. And the question is, does it equal 15 squared? 81, 144, 225. 225 equals 225. If the Pythagorean theorem works, then it's a right angle. So we started off with a right triangle. If it's a right triangle, Pythagorean theorem always works. If the Pythagorean theorem works, then it's a right triangle. And that's called the converse. Good. We're going to go back to radical land again. Now, I don't know who makes the rules in radical land, but one of the rules in radical land is you can't be a radical and be in the denominator. So if you had 7 over the square root of 2, apparently, according to their zoning commission, or all the radicals got together and made up some rules, you can't have this guy be in the denominator. So how are we going to make a whole number? You can have whole numbers in the denominator, but you can't have radicals. So how do we change the form without changing the value? What do you think? What can I multiply by this that would make it a whole number? That's the key. Right there is the whole key to this whole lesson. What do I multiply by that to make that a whole number? If I multiply it by 2, it just becomes that. Square root of 2. Let's try it. Multiply square root of 2. But I can't just go multiplying the denominator by square root of 2. I have to do the numerator as well, because the square root of 2 divided by the square root of 2 is 1. So what I'm really doing is multiplying it by 1. This is like back in old fraction day when you multiply 2/3 times 4 over 4, and you get 8 over 12, right? It's a different form, but it's still the same value because we just multiplied it by 1. Okay. Well, let's see what happens. What's the square root of 2 times the square root of 2? The square root of 4, which is 2. So now we've got the 7 square root of 2 over a whole number 2. Now, if you want, I'll do the first one. But after a while, you should know If you multiply the square root of 4 times the square root of 4, you get the square root of 4. You get 4. Square root of x times the square root of x is x. Square root of 2 times the square root of 2 is the square root of 4, which is 2. Okay, you get that? So this looks different, but it's the same value, just a different form. Got that okay? What if we'd multiplied it by the square root of 3? Would that have worked? Then we'd have had 7 square root of 3 over the square root of 6, and we're still in bad shape in radical land because we can't have radicals in the denominator. Okay, let's try a different one. 3 over the square root of 5. The radical police are coming for him. What does he have to do to change his shape?
I can't talk.
That's okay. Do sign language.
Five.
Multiplied by radical 5. This is always the easiest way, right? Just multiply it by itself because that becomes 5, and this becomes 3 times the square root of 5. Then we're okay. All right? But there are some cases where you can use this simple formula, or you can think a little bit more to make your work easier. I'm going to solve this problem 2 ways. The first way that we've been doing, we would just multiply this by the square root of 8, correct? And then square root of 8 times square root of 8 is the square root of 64, which is 8. So we've got 4 times the square root of 8 over 8. Does this look like it's in its reduced or simplified form? No, because just looking at the whole numbers, we could divide that and make that over 2, right? Like a 1 over 2, but the 1 is just absorbed in that. Is that okay? Could we simplify the square root of 8? Are there any whole number factors in 8? What?
2 and 4.
Okay, so we could make the square root of 8 the square root of 4 times the square root of 2, correct? And we still have 2 in the denominator. Now what's the square root of 4? 2. What's 2 divided by 2? 1. So that's the answer. But that was a lot of work, and it would be even more work if you were doing it on your yellow pads. I have a dry erase marker. I don't have to write everything again. I can just erase, right? Okay, that's it. Let's look at a little shorter solution. Square root of 8. Do you remember all of our perfect squares? Give me the perfect squares again. We're going to start with, we'll skip 1. What's 2 squared? 3 squared? 4 squared? 5 squared? Okay, you getting the idea? What could we multiply times the square root of 8 that would give us any of those? What? Square root of 2. If I multiply this by the square root of 2 over the square root of 2, this becomes the square root of 16, which is a perfect square, which would be 4, right? We just bring this guy over, 4 over the square root of 2. We divide, cancel, whatever you want to call that, and the answer is square root of 2. Which was easier? That was easier. Which was most accurate? They both were accurate. So you can always just multiply it by the number itself, but you may have to do more reducing. That's all I'm suggesting. If you can find a shortcut, use it. All right? Okay. Let's do one a little bit tougher. And I just said okay again. 3 over the square root of 2 plus what is that? 5 over the square root of 3. I better make sure. Yes. Okay. This is as hard as it gets, so don't think I've got more things up my sleeves, okay? This is as hard as it gets. First of all, we're in bad trouble because we've got radicals in the denominator. We have to get rid of those. But we also are adding 2 fractions, and we can't add 2 fractions unless they have the same denominator. But first, let's get rid of the radicals in the denominator, and then we'll deal with it as a fraction problem. So it's 2 levels here. What would we multiply times this one to get rid of that radical sign? Not 2, square root of 2. I'm going to do it out here. And what am I going to multiply by this one? Square root of 3. Okay, this gives us 3 in the denominator and 5 times the square root of 3 in the numerator. This gives us a 2 in the denominator and 3 times the square root of 2 in the numerator. That all clear, okay? It's a little bit tricky. I usually like to have the square root on this side of the number so you don't absorb them and make that square root of 6. But that's a number, that's a radical, that's a number, that's a radical. Okay, now what do we do? Who remembers the rule of 4? When you're adding two fractions, remember the rule of 4? All we have to do is multiply 3 times both of these. 3 times this would be 9 times the square root of 2. 3 times the 2 is what? 6. Then multiply the 2 times both of these. 10 times the square root of 3 over 6. Getting closer? All we have to do now is combine them. There. Isn't that easier? And that would be our answer. 9 times the square root of 2 plus 10 times the square root of 3 over 6. Done. So we've gotten rid of the radicals in the denominator. We found the common denominator. Now, how would you find the common denominator if you didn't know the rule of 3? I'm sorry, the rule of 4. You guys didn't do my epsilon book, okay? But the rule of 4 is really slick when you're doing fractions. All you do is you take this number and multiply it by both of these. So in a sense, you're multiplying this by 3 over 3, right? Then you take this number and multiply it by both of these, which is like multiplying by 2 over 2. And that's how you get this over 6 and this over 6. But you know that if you multiply the 3 times the 2, you're going to get a 6, and that'll be a common denominator. Every time, no exceptions. And all the math scholars are now going, ooh, if I can just find one exception, I can prove him wrong. You won't. That always works, okay? There you go. You know how to do this. $45 plus 45 is what? 90 plus 90 is 180. So if you have a 45, 45, 90 right triangle, which you could think of maybe as half of a square with my little faint ghost square over there, ghost lines, what would you think about the sides opposite congruent angles? We talked about this once briefly. They would, because if this is a square, first of all, we know that all 4 sides are the same. But we also know that if we cut a square directly, we bisect the angle, we get 45, 45, 45, 45, and we're going to have all sides the same, okay? So the 2 legs are going to be congruent, and we would put slashes, the same amount of slashes in each leg to show this, okay? Now there's a relationship between the legs of a 45, 45, 90 and the hypotenuse. But instead of just telling you, we're going to figure it out. Let's make this a 6. If this is 6, what's this? What would be the hypotenuse? Well, we'd have 6 squared plus 6 squared equals hypotenuse squared. 36 plus 36 would be 72 equals the hypotenuse squared. Then we have to take the square root of both sides to find the hypotenuse. The perfect square that we would see in 72, well, what do you see? Do you see a 4? There is a 4 in there. How about 9? There is a 9. But let's keep going until we find the largest perfect square. How about 25? I skipped. 16, no. 25, no. How about 36? Yes. So we could make this the square root of 36 times the square root of 2, and the square root of 36 is 6. So this would be 6 times the square root of 2. Okay? Let's do another one. Let's make the sides 10. The legs, I'm sorry. The legs are 10. Question is, what's the hypotenuse? So the hypotenuse squared equals 10 squared plus 10 squared. What's 10 squared? 100 plus 100 is 200. And I'm going to show you a little shortcut here. I could put that as 100 times 2, correct? Okay, now I can take the square root of both sides, and I get hypotenuse is the square root of 100 times the square root of 2. What's the square root of 100? 10. Okay, do you see a pattern yet? What's the pattern?
They're the same number as they were added. So if it's like 10, then it's 10 with the square root of 2.
Okay, if it's 10, it's 10 times the square root of 2. So if this was rocket ship and this was rocket ship, what would be the hypotenuse? Ship times the square root of 2. Very good. Why do we use numbers or things that aren't numbers? Is because then it applies to all situations. It's called a variable. So let's try doing our little thing again with a letter. We'll call this A and this A. And you and I think that this is what? A square root of 2, right? But let's prove it. A squared plus A squared equals hypotenuse squared. That would be 2A squared. Sorry. 2A squared equals hypotenuse squared. Now I've got to take the square root of both sides to find the hypotenuse. I get the square root of 2 times the square root of A squared. What's the square root of A squared? A. So our answer is what we predicted, A times the square root of 2. So you found this. So whenever, let's say that you know that this is 45, 45, 90, and I say, okay, this is 13 times the square root of 2. What's the length of each leg? 13. If this is 1.35, what's this? 1.35, right? This is pretty slick. But what if this is a whole number and there's no square root of 2 in it? How do we find it? Well, let's just do this. Let's do leg 8. So we know leg squared plus leg squared equals what? 8 squared, right? So this would be 2L squared equals 8 squared. So now what are we going to do? We're trying to find L. Let's go ahead and multiply this out. Let's make that a 64. Then we're going to divide both sides by 2, right? So we get L squared equals 32. Now I've got to take the square root of both sides to find L equals the square root of 32. What is the square root of 32? Square root of 32, we've got to simplify. Is there a 4 in there? Yeah. Is there a 9 in there? Yeah, no. Is there a 16 in there? Ooh, is there 25? Too big. Okay, so let's stop with 16. So that's the square root of 16 times the square root of 2. And what's the square root of 16? 4. So it turns out our legs are 4 times the square root of 2. Okay? Now, let's go back and check it and see if this works with what we thought. We thought that the leg times the square root of 2 would give us the hypotenuse. That was kind of our goal, right? So let's stick in 4 times the square root of 2 times the square root of 2 and see if that gives us an 8, because that's what it should give us. So what's the square root of 2 times the square root of 2? 2. It's a square root of 4, which is 2. 2 times 4 is 8. It works. So you can still do it. And here's a shortcut what you could do. You could say, well, if the leg times the square root of 2 equals the hypotenuse, then if the hypotenuse is 8, I just divide both sides by the square root of 2, and that will work. then you have to simplify. There's several different ways to arrive at the correct conclusion, but when you're all said and done, the leg times the square root of 2 in a 45, 45, 90 right triangle will give you the hypotenuse. Feel comfortable with that? Okay. We have another kind of special. Now, you can have two kinds of special, and they'll both be special. Okay. When your parents tell you you're special, you really are special. But we tell all of our kids they're special. All right. So this is another special right triangle. This is the smallest angle. This is the larger of the two. What's the relationship between these two angles? They equal 90. They have to because we've got a right triangle again. See, 30, 60, 90. So these two are going to be complementary because they add up to 90. But this one's twice the size of this one, isn't it? So this probably isn't an accurate picture, but this side should be our longest leg. This should be our shortest leg, and this is called our hypotenuse. So what we're going to try to find out is if we know that, and these are accurate numbers, if this is 4 and this is 4 times the square root of 3, what would be the hypotenuse? We're going to do two problems and then look for a pattern like we did in the previous lesson. 4 squared, leg squared, plus 4 times the square root of 3, the whole thing squared, equals hypotenuse squared. Don't just square one part or another part, do the whole thing. Parentheses are good to help you to remember to do that. This is 16. What's 4 squared? 16. What's the square root of 3 times the square root of 3? 3. So I'm just going to put in 16 times 3. Now we can add this up. 16 plus 48 is 64, and that's equal to our hypotenuse squared. If we take the square root of both sides, hypotenuse is 8. Okay? Look first. What do you see? What's starting to form in your mind, the relationship between legs and hypotenuse?
Is the hypotenuse always twice the length of the shorter leg?
Okay, well, let's hold that thought. The hypotenuse looks like it's twice the length of the short leg. Let's do another problem and see if we arrive at the same conclusion. We're going to make these 7. We don't know what that is. So this is 7, this is 7. So the leg squared plus leg squared equals the hypotenuse squared. This would be 49. This would be 7 squared, 49 times 3 equals hypotenuse squared. I don't know that, but I know 3 times 50 would be 150 minus 3, so that's probably 147 plus 49. And if we add this plus this, I don't know that either, but I'm going to guess it's 196. Yeah, it should be. Hypotenuse squared. Take the square root of both sides. Hypotenuse equals, what's the square root of 196? 14. Okay, 14. Did it follow? Did what your original observation follow through again?
Yeah.
It turned out it did. And if we wanted to, we could do this with a variable. This is twice the size of the short leg. Let's try side times the square root of 3 and see what we come up with here. Okay? Side squared plus side times the square root of 3 squared equals hypotenuse squared. We get side squared plus side squared times square 3 squared is 3. So 3 side squared. We get 4 side squared equals hypotenuse squared. Square root of both sides. Square root of 4 is 2. Square root of s squared is s equals hypotenuse. Oh, look at that. It works. The short leg doubled The side opposite the 30 degree doubled will give you the hypotenuse. You see another relationship in all of these. If you multiply this times the square root of 3, you get this one. This is the 30, 60, 90 right triangle. Let's do some more problems. Well, I've got to get my glasses on so I can see them. There they are. Let's solve for the long leg, just to make sure. If this is 5, and this would be what? If this is 30, and this is 60, this is a right triangle, what would the hypotenuse be? 10. Long leg, we don't know, so we're going to solve. So we've got 5 squared plus long leg squared equals 10 squared. This would be 25. 100, long leg squared. Subtract 25, we've got long leg squared equals 75. Square root of both sides. Long leg equals the square root. What is that sign right there? I think I lost my coordination. Square root of 25 times the square root of 3. What's the square root of 25? 5 times the square root of 3. It works. You see that? So if you know the short leg, you double it to find the hypotenuse. You multiply it by the square root of 3 to find the long leg. Groovy? Like an old-time movie? And every time I look down at the book, you're going, yes, but he's going to make them tougher. I am. Sorry. But it's the same formula. So short leg times 2 equals the hypotenuse. Short leg times the square root of 3 equals the long leg. These are givens. So what if our long leg is not something times the square root of 3? What if it's 10? Can I find the short leg and the hypotenuse just given this information? What say ye, class? Yeah. Will it be easy? No, you're correct. But let's try it. So the short leg times the square root of 3 is going to give us 10. Well, that's easier than doing the whole Pythagorean theorem, which we could have done. So what we're going to do now is just divide both sides by the square root of 3. Can I leave it like that? So I multiply both by square root of 3 over the square root of 3. So that gives me 10 square root of 3 over 3. Done. Okay, how do I find the hypotenuse now? Double it. 20 square root of 3 over 3. Done. It's not as bad as you thought, right? It would have been hard to figure, though, if we had to use Pythagorean theorem and subtract and all that. But because we know these two relationships, we can solve even hard problems like that. Okay, and the converse says, the converse, if I draw a triangle and I say that's 8 and that's 16, what kind of triangle is that? Absolutely, because the short leg is half of the hypotenuse, or this is double this. So what would the long leg be? 8 square root of 3, and we know that that's 30 and that's 60 just because we noticed one relationship right here, right? How about if I walked in someday and I said, this is 30, right angle, that's 6. Tell me all the rest of the information.
The other angle is not 60.
Yes, good.
The hypotenuse is 12.
Good. That's 90.
The long leg is 6 times square root of 3.
You guys are a good team. 4 people answered 4 questions. Awesome. End of lesson. Peekaboo. I'm going to read to you now. I'm Grandpa Steve with my little reading glasses. But this next lesson on axioms, postulates, and theorems. This is a little bit hard to follow, and it doesn't satisfy my sense of logic and truth, but I'll tell it to you anyway. You start with what we observe to be true. We've called that already a postulate. Now we postulate, or we make these observations like two vertical angles are congruent. I think that's accurate. Would you agree? I could measure 1,000,000 of them, I could observe it, I can look at it, but I can't prove it unless I have something to prove it with. So to have things to prove with, you have to create postulates. So it seems like it's a little funny, things that you can't prove, you use to prove things that are true. Anyway, for whatever reason, that's what we call these things. Now, I'm going to read through them quickly because it's almost a compilation of everything we've been studying in the previous lessons. Vertical angles are congruent, number one. Number two, a bisector divides an angle into two congruent angles. Do you agree? A midpoint divides a line segment into two congruent segments. A rectangle has 4 right angles and 2 pairs of parallel sides. Now, I don't have to read all of these, but I'm just going to read some selected ones. A trapezoid has 1 pair of parallel sides. If 2 parallel lines are cut by a transversal, alternate exterior angles are congruent. The measures of the interior angles of a triangle add up to 180 degrees. These are all things that we've been observing and working with and satisfying to our satisfaction that they're accurate. There's 3 new ones, though, and they are called the properties of symmetry, reflexive property, and the transitive property. And when you look at them and I write them, you're going to say, if not out loud to yourself, duh. So here we go. Here's the property of symmetry. If A equals B, then B equals A. Let's all say it together. Duh. But that's obvious, right? But you're going to find out because in successive lessons we're going to be proving triangles congruent. And we're going to be stating what looks like the obvious. But you have to state it. It's as if you're in court and you have to at least enter it into the body of data that you're going to use to make your arguments. Okay? Here's another one. The reflexive property. This is even more duh. Very good. I didn't even have to orchestrate that one. Let's try the next one. The next one's a little bit more sublime. If A equals B and B equals C, then A equals C. Okay? That's just a short duh. Let's just do a duh. Okay. That one at least makes you think a little bit, and we're not just stating the obvious. Now, all of these we have called postulates, axioms, and now we also have converses to all of these. And this is a critical point that you have to recall. I'm going to say one, and you tell me the converse. If 2 angles have equal measures, they are congruent. The converse would be?
2 angles are congruent, therefore their measures are equal.
If 2 angles are congruent, they have equal measures. Very good. Another one. A regular polygon has all sides congruent and all angles congruent. The converse would be?
A polygon that has all the angles and all the measures the same is congruent.
Is regular.
Regular, sorry, yeah.
No, you're good. So if all the angles and all the sides are congruent, then it's a regular polygon. They go both ways. Try this one. 2 angles whose measures add up to 90 degrees are complementary. The converse would be, if 2 angles are complementary, their measures add up to 90 degrees. This is logic. Aren't you taking a class in logic? This is, and you've probably seen some of these things in logic, haven't you? Okay. But a lot of proving triangles congruent does bring in, it reinforces what we've been learning in geometry, but it also teaches you how to do logical progression of thinking and don't assume even the obvious. State everything. Last one. An isosceles triangle has 2 congruent sides. The converse is?
A triangle
Very good. If a triangle has two congruent sides, then it's an isosceles triangle. Nice job. I have two triangles here that I have drawn freehand. I didn't trace them, and you can tell. But we're going to assume that they are congruent. They're identical. The only thing that's different is the labeling. So what we're going to look at is this word called corresponding. Which point, and I'm going to call this triangle 2, triangle 1, which point corresponds to point A in this triangle here? D. Which point corresponds to B? Which point corresponds to C? Okay. Because if we were to take this triangle and pick it up and superimpose it on this, A and D correspond, angles 1 and 4 correspond. B and E correspond, 2 and 5 angles correspond. Right? So in order for two triangles to be congruent, how many parts are there in a triangle? There's 3 sides, and there's 3 angles, and all 6 of those have to be congruent. Now, this is pretty easy to see, but what if I had inverted this, and so then the E was down here and the F was here? It would still be the same triangle, but it's a little bit harder to track, isn't it? Because you don't see it so clearly. Or if I spun it this way and flipped it. So sometimes you almost have to draw another triangle, because I'm going to ask you questions like, what corresponds to line segment AB? Which line segment corresponds to that? So we're going to put little arrows to mean that they correspond. Which corresponds to BC? Which line segment down here? EF. And which corresponds to AC? DF. And it's good to go in the same direction if you can. Which angle corresponds to angle 1? Angle 4. And and the list goes on. I could also do things like, I could say triangle ABC corresponds to triangle what? ABC, so I went up and over, so I'm going to go up and over, DEF. What if I did this? Triangle CAB corresponds to triangle what? Yeah, if I went CAB, I could do FDE. Good. Getting this okay? So this is corresponding. Now let's do a little trickier one, though. Let's do one where the two triangles are congruent, but they're rotated around the axis. So if this was A, B, C, and this is D and E, and we're going to make these right triangles, AC corresponds to what? EC. Out to the center, out to the center, correct? Because if you were to take this and flip it up, you'd have to do like that. Some people really struggle with this. So if you're one of those people, you might have to almost cut this out, draw it, and pick it up and put it over here so that you can see that the E, if you flip this and turned it, the E would be up here, the D would be over here, the C would be on top of itself. Okay, how about this one? DE corresponds to starting at the right angle, going away, BA. Take your time on this, but this is good. Okay? So we're looking at corresponding parts of congruent triangles. Now we're going to go to a remote part of the jungle and study remote interior angles. We must be in the interior of the Congo. This is a triangle and a line. I'm assuming this. I'm going to tell you that right up front. We've got angle 1, angle 2, we've got angle 3, and we've got 70 degrees. These are the interior. This is the exterior angles. We call them remote because they're not adjacent. See, 3 and 70 degrees would be adjacent, but this is way far away. Sorry, best I could do it. They're remote, okay? Don't think remote control. Remote means they're far away from adjacent. So what's the relationship between these remote interior angles and this exterior angle here? If this is 70 degrees, what is angle 3's measure? 110. How do you know that? Supplementary. They make a straight line and they add up to 180. What would angle 1 and angle 2 add up to? 110. How do you know that?
Well, because it's a triangle and triangles need 180 degrees. We already have 70.
Okay, so triangles also need 180. Just like lines need 180, triangles need 180. So if we have angle 1 plus angle 2 plus angle, well, we'll just put the 70 in there. We know that these have to add up to 180 degrees. We've already found out that angle 3 plus 70 degrees equals 180, right? So just looking at this, what can you deduce? Well, let's subtract the 70 from both sides. Make it a little easier for you, perhaps. Correct? Could I say this? Now, this looks to me like a property that we just learned. If angle 1 plus angle 2 equals this, if A equals B and B equals C, or if A equals B and B equals C, is this true? Because these two add up to 110, this is 110, so it turns out that the exterior angle is the same as if you add the two remote interior angles. So let's do a problem, see if you can figure this out. Let's draw another triangle, and this is going to be 74 degrees. And we're going to make this 44 degrees. Tell me the other measures. What would this be over here? 106, because they have to add up to 180. What would this one be here? 62, because these two have to add up to that, correct? So if we already had 106, so if we'll call this alpha, if alpha plus 44 equals 106 degrees, subtract 44, alpha equals 62 degrees. And here's our statement. Maybe we'll call it another postulate. We conclude that the measure of the exterior angle of a triangle is equal to the sum of the measures of the two remote interior angles. Do you agree with that? Okay. We're going to talk about proving triangles congruent. This is our first time. We've been laying the foundation for several lessons, but now we're going to talk about it. When I first taught geometry, this used to be the main thing that you studied in geometry, was proving triangles congruent. In fact, if I was to get a room full of students of mine or adults in our generation and say, how many of you like geometry, you'd probably find about half liked it and half disliked it intensely. And then if I said, what is geometry? They would say, proving triangles congruent. And there's a certain part of the population that liked the visual nature of geometry, and they liked the logical part, and they said, I really like this class, let's take more. And then the other class couldn't wait to get out, the other half, okay? And it's almost 50-50, and I've done this for years for larger and smaller audiences, and I usually get about the same ratio. I put it at the end of the book because it does have value, but I don't believe it is the preeminent aspect of geometry. Geometry means measure of the earth. So when I first taught it, we were fortunate if we even made it to area, perimeter, and volume, which was at the end of the book. And so I did it this way on purpose. I also found out that oftentimes logic is something that comes with age. Don't be offended by that, but sometimes a little bit of years will give your brain a chance to mature a little bit more, and you can do logic a little bit easier than you can when your hormones are all stirred up. Okay? So if you happen to be struggling with these proofs, you might even want to just stop and do some Algebra 2 or something and come back maybe next year, because sometimes just a few months will help you to see it a little differently. So don't be discouraged by proofs, but they are different, because there is the geometric aspect of it. We're going to be using lines, points, planes, and all that. But there is a logic to it. So that's just a little bit of an exhortation. What do we know so far about triangles and their angles? Let's say that this is 80 degrees and this is 60 degrees. What do we know about this angle here? It's 40 degrees. How do you know that? You need 180, so this has got to be 40. Every time. There are 6 parts of a triangle. There are 3 angles and there are 3 sides. But we just learned one thing real quickly, that you don't really have to know all 3 angles, because if you know 2 of the angles, you can deduce the 3rd one. Correct? In fact, when we get later into right triangles, you only have to know 1. Because you already know the 90, so if you know that that's 37, that's got to add up to 90, so this has got to be 53. You know this, correct? So just learning 2 angles takes care of all 3. What about sides? I'm going to construct a triangle using these blocks, a 4 and a 5, it's our old buddy, the 3. And even though I want to put it up here, I have to bring it down here to connect the corners. Now, do you think I can make a different triangle out of these 3 blocks than this one? Well, I'm going to try. I'm going to put the 4 over here. I'm going to put the 5 bar over here and try. That doesn't work. I end up having to bring this up again, and I bring this over, I bring this up. And it turns out if I was to take this and pivot it around, it still is going to be the same triangle, correct? And so our first one that we're going to look at is called the side, side, side postulate, because what it says is if you have 3 congruent sides of one triangle and you have another triangle with the same 3 sides, those triangles are going to be congruent. Every time. You don't even have to worry about the angles. In fact, if you were to measure these angles, you would find out that that's 90, that's 90. If I'm not mistaken, that's 57, and that's 43, 57 and 43. So if you just have the 3 sides, you don't have to get all 6 pieces. You've already got all 6 by just getting the 3 sides. And once you've proved the triangle's congruent, then you can go it further and say, and the angles would also be congruent, because if the triangles are congruent, the angles are congruent. Yes?
It wouldn't be 57 and 43, because that's...
You're right. Thank you. 57, what would it be?
190, I think.
No, it's like 53 and 37, maybe, something like that. I forget, but the 3, 4, 5 right triangle, I used to know those. Thank you for correcting that. So it's not 57 and 43. But they do have measures, but whatever this measure is, that's identical. Whatever that measure is, that's identical. Whatever that is, that's identical. Because if the triangles are congruent, all 6 pieces are congruent. So all you have to really do is find 3 sides, and all 6 are taken care of. Take a deep breath. Get more blood to your head if you need to. Put your feet up against the wall. For some people, I'm telling you, this is right down their alley. They said, I like this. Other people, it's really takes some energy. So let's just take some time, and that's the nice part about DVDs. You can review them and watch them again. Just don't pause it when I'm making a bad face. There are 5 components to a proof. The 5 components are, you've got a figure, you've got givens, in this case a given, and you've got what your objective is, what you want to prove. So think of this as you're a lawyer and you're gathering data. I don't know if you've ever watched law on television or anything. It's been on for years. But these law shows. And so lawyers have people that go out and they collect and they research and they get all their arguments together. But until, you ever see how they enter this into the court record? You ever notice how they do that? Until it is spoken in court and entered into the record, they might know all this stuff in their head, but it doesn't play a part in the case. So down here, this is where all of this information and everything that we're thinking has to be written out, and you can't assume anything. You can't assume because it's up here, it's down here. You have to write it step by step. Don't assume anything, even if it's obvious, all right? So here's what we're going to do. We're going to start off with our statement. QRST is a rhombus. QRST is a rhombus. How do you know that? Because it's given. That's part of what was provided. So that's your reason. You just say, well, it was given. Now, we only know one way to prove a triangle congruent at this point in our career. What is that way? Side, side, side. If we can find 3 sides congruent, so if we can find 3 sides of this triangle and 3 sides of this triangle congruent, then we can do what we're trying to do, which is to prove that triangle QRS is congruent to triangle QTS. That's our objective. So what I like to do is put in the objective, because my last statement is going to be triangle QRS is congruent to triangle QTS. Now, I'm not sure why now, but probably it's going to be side, side, side. So we'll go ahead and put that in there in parentheses. Side, side, side. So what do we have to do to prove that these 2 triangles are congruent? What do we have to find?
We have to find that all the sides are.
We have to find 3 pair of sides that are corresponding and are congruent. So which one do you want to start with? QS.
QS is equal to QS.
QS, and we can put line segment is congruent to QS line segment. What's the reason? You remember those duh that we went through?
Because it's the same side.
It's the same. Remember A equals A? That's called the reflexive property. And you will use that one more than you think, because if you share a common side. So what we could say right away is those 2 sides are congruent to each other, correct? Because they're congruent to each other, because they're congruent to the self. Now you could, if you want to visualize, pull this apart a little bit, but because it's the same line, they're congruent. Reflexive property. We've got 1 side done. Good. We need 2 more sides. Pick another one. Okay, which side is congruent to RS? QT. We could do QT or we could do ST. Doesn't make any difference. You know why? Because this is a rhombus, and all 4 sides are the same. But we could say RS, line segment RS, is congruent to line segment, what did you say, QT? That's a QT. What's my reason?
It's a rhombus.
It's a rhombus. So what you say is definition of a rhombus, which is one of our postulates, that if you have a rhombus, you've got 4 congruent sides. Okay, we've got 2 sides. We need 1 more. How are we going to get it?
Same thing with QR and TS.
Okay, we can do QR and TS. And the reason is, same thing. Now we've got three sides congruent, and we can now confidently state that these two triangles are congruent because of what we've already discovered about the side, side, side postulate. Yes?
Wouldn't we only have to prove two sides are the same? Because if two sides are the same, then the third side wouldn't that have to be the same?
Hold that thought for one more proof, please. That's a good question. Because like angles, if we got two angles, then the third would be the same. So would it follow that if we had two sides, the third side would be the same? Well, we're going to look at that in just a moment. That's a good segue. The question that we were just asked was, if you have two sides of one triangle congruent to two sides of another triangle, are those triangles congruent? Just with two instead of all three, like in side, side, side. So I've got two sides here of this triangle. I've got a 4 and a 5 bar. I've got another 4 and a 5 bar. And so I could do this for this triangle. And I could do this with this triangle. So what do you think? That's got a 4 and a 5, and that's got a 4 and a 5. What would I need to have stated that would make it with two sides? You can do it with two sides, but you need one more thing. The angle. Because if you were to tell me this angle has to be 90 degrees, then I've got to have this one has got to be 90 degrees. And as long as this angle in between the two sides, this is real important. Because if the angle was this angle out here, it could be like this. But these two sides here, it's got to be in between. So if these two angles are 60 degrees, for example, would they be the same? Yeah. No matter what I put there, it's going to be the same piece there. If I made the angle 120, and this angle is 120, whichever piece goes there is going to go there. You see that? So we have another postulate then. We have a side, and we have a side, and we have the angle, so we call it the side angle side, or SAS. So we have the side angle side or the SAS. That help? So if you have just these three, side, angle, side, then the other side's going to be the same, those two angles are going to be the same, and both triangles are congruent. It's a good thing you asked that because we're going to need SAS in this guy here. So the first thing we're going to do is see if all of our components are here. Whoa, I wrote out the word statements. I crossed it out. All right. We look at this drawing. What do you notice by looking at it? Well, the given is that H is a midpoint of DF and GE. So the first thing I'm going to do is put in some little slash marks. You can do whatever you want. You can put stars there, rocket ships. Doesn't make any difference to me. Okay? So these two sides are going to be the same because a midpoint divides a line segment into two congruent parts. And so these two are going to be congruent, and these two are congruent. Correct? Okay, you got two sides. How are we going to get an angle? Yes?
You know that the two angles at H are the same because they're connected to lines.
These two are the same. How do we know?
They're the same line.
What kind of angles are these called?
Vertical angles?
Vertical angles. So we'll put little slashes there. So now we've already thought it through. We've backed up, looked at it, and we've found a side, angle, side, and a side, angle, side. So that would work. But it doesn't convince anybody until it's entered into the record of the court. So let's enter into the record. First statement is what? H is a midpoint. Da, 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 da. Reason? Given. We like those given ones. Okay? What's going to be our last point?
Triangle BGH is congruent to triangle FEH.
That the two triangles are congruent. Notice the order, D, G, H, F, E, H. Okay? Our reason is probably going to be side angle sides. We'll write that in there. So now we've got to write down a side and an angle and a side. You don't have to put it in that order, but it helps me to think of it logically. So what's the first side we're going to put in? HF and HD. What's that? High definition? Congruent? Why? Why do we know they're congruent? And I'd probably just put definition of a midpoint. Okay, definition, midpoint. Where's our angle going to be? Well, we can't say angle H because that could be this, it could be this, it could. We have to use the letters. So we're going to say angle GHD. How about that? GHD, and then EHF. H is still the midpoint. I mean, you can see it's the vertex. But these are congruent because of, right, vertical angles, or definition of vertical angles. And then we need one more side. It's going to be this and this. The reason is definition of a midpoint. This is all written out in your book. Does that help? I don't know how to give any advice except to just do a bunch of them, but think it through. State everything. Don't assume anything, even if it's obvious. And this proof is going to be your last line. Usually your givens are your first line, but there's no order necessary up here. Do you want to put it all in there? We need a couple more postulates in our bag for solving or proving triangles congruent. So far we have side, 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 and we have side, angle, side, and now we're going to deduce. I don't know if you've found this out yet, but it's hard for me to do this with people that are watching on DVD, but I like to let you figure things out yourself if you can. So if you want to, see if you can get your 6-bar out, or just draw a line that's a certain length. And then if you have a protractor, take your protractor and draw a 50-degree angle and a 70-degree angle. And say, I'm going to take this down here and pull out a little protractor, because this is a small problem. And I'm going to find out 50 degrees is about here, and 70 degrees is about here. And then what I would do is I'd get my straight edge and I would connect them, and it's going to go like this, and it's going to go like this. And if I did the same thing with this piece over here, guess what I'm going to get? The same triangle. Because if I'm telling you where, the measure of those angles, then that side can't go up and be a right angle. It's got to go 50 degrees. This one can't go up here, it can't go here. It's got to be 70 degrees. I'm locking in where those sides go, and those sides are going to intersect up here. And you could do that 10 times. You're going to draw 10 congruent triangles. What do you think we're going to call this theorem?
Angle, side, angle.
Because we have an angle, we have a side, we have an angle. We're going to call it angle, side, angle. But the side, catch this, the side is included. The side is in between the two angles. Now, having said that, now I'm going to say something else. You might say, well, you're being contradictory. What if you had your 8-bar? Get out your chocolate 8 if you want. And you're going to draw a 65-degree angle here. And you're going to draw a 40-degree angle up here. And you might say, well, you didn't tell me how far to go, right? I could just go up here and do a 40, or I could go up here. What did the first thing we learned about corresponding parts of triangles?
The other angle is 75 degrees.
Because if I give you 2 angles, I'm really giving you 3. Because if that's 65 and that's 40, that's 105. This has got to be 75. So this is not as vague as you think, because if you've got 2, you've got 3. If you've got 3, you've got angle, side, angle again. But instead, we call this AAS, which is angle, angle, side. I like to do things a little bit differently. I have a brain that thinks differently. So what I call both of these is the I combine them, because you've got angle, angle, side, and you've got angle, side, angle, whatever works for you. But if you've got angle, angle, you've really got angle, 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 don't you? And if you've got angle, side, angle, you've really got angle, side, angle, angle. So if you've got 2 angles, you've got all 3. All you need is one side to work from, and everything else falls in place. This is sometimes called the amplified parallelogram theorem. I don't think requires that big of a moniker, but it is something that you're going to use a lot. But one thing before we get into it, we need to state. You notice in this one, the given is that PLGR, this quadrilateral, is a parallelogram, which means these sides are parallel, these sides are parallel. We're asked to prove not that 2 triangles are congruent. We're asked to prove that PR and GL are congruent, and that RG and LP are congruent, that the sides are the same length. So how are we going to prove that? What do you think? How are we going to prove that these sides are congruent?
Well, are we going to have to prove that the 2 triangles are congruent?
That's the first step. The first step is to find out that the triangles are congruent. And then if we know that 2 triangles are congruent, we know that all 6 pieces that correspond are also congruent. And that's going to be our final statement. In fact, I'm going to use like an acronym. I'm going to say, instead of writing this out because you're going to use it a lot, this means corresponding parts of congruent triangles are congruent. You can use an A there if you want, but I like the R, a little joke. So corresponding parts of congruent triangles are congruent. So if the triangles are congruent, all 6 corresponding 3 angles and 3 sides are going to be congruent. So our goal then is not, this is going to be our last step, right? I'm not going to write that all out, but I'm just going to circle it. This is going to be our last step. But the step before it is going to be to say that triangle PLG is congruent to triangle RGP. Now, we don't know why, so let's go through it. First step, got to state everything. Doesn't make any difference what's up here. You got to put it down here. It doesn't count. Yes?
We're going to have to put the given statement down.
The given, that this parallelogram, PLGR, is a parallelogram, given. All right. Now, how are we going to figure this out? Well, first of all, let's do the easy one. PG is congruent to PG because of reflexive. Remember that good one? So PG is congruent to itself. So now we've got a side. If we can just get 2 angles, we are all set, because then we can use angle, side, angle, or angle, angle, side. Which 2 angles?
Angle RPG and angle
RPG. This one?
and angle PGL
PGL.
are congruent because of the alternate interior line.
Perfect. If you've got 2 parallel lines cut by a transversal, alternate interior angles are congruent. So what we just said, I'm just going to put a 1 and a 2 here to save time. Angle 1 is congruent to angle 2 because 2 parallel lines cut by transversal, alternate interior angles, congruent. I need one more angle. Yes? RGP. LPG. Same reason, right? But in this case, you could say 2 parallel lines cut by transversal, alternate interior angles are congruent. That would give us the second angle. I will call that 3 and 4. Same reason. The two triangles are congruent because of angle, side, angle. Angle, side, angle. And then you state, then these two line segments are congruent. These two line segments are congruent because corresponding parts of congruent triangles are congruent. Yes?
If they're congruent, then you can't, the letters on the bottom for proving that they're not in the right order then.
Well, what I would do is I would say PR is congruent to GL and RG is congruent to LP. And the reason would be,
The one before that, just proving that the triangles are, one of them, they're not in the same order.
oh, not in the same order? So we've got P, LG, and PRG or GRP. Yeah, maybe it should be GRP. Okay. So it'd be good to put them so that they correspond. What do I have in the book there? PRG and GLP. PRG and GLP. Good job. If we're going to prove triangles congruent, that we already know that they are right triangles, it makes our job a lot easier. So far, we know SSS, which is the three sides. We know SAS, side, angle, side. We know angle, side, angle, and angle, angle, side. Correct? By the way, if there's other combinations that have those letters, you might want to try yourself and see whether they couldn't be true. I mean, you could do SSA, two sides and an angle, see if that would be congruent. Or you could do angle, angle, angle. Try that one. But just experiment if you want. But now we're going to do right triangles. And right triangles have legs, and they have hypotenuse. They have two angles, but you already know one of the angles, correct? In fact, because of the Pythagorean theorem, if you know these two sides, you can find the third side. If you know these two sides, you can find this side. So if you know two sides, you really know all three. That's different than a regular triangle. Only right triangles does the Pythagorean theorem work for. And because you already know one angle, if you're given just one angle, you really know all three angles. Because if it's a right triangle, that's one. And then if you know that this is 40, got to be 50, right? So let's look at our new, what we would call, proving right triangles congruent. If we had hypotenuse and one leg, would that be enough? Well, if we had the hypotenuse and one leg, we could do Pythagorean theorem and find the third leg. So that's really like having all three sides. So I'm going to say that the hypotenuse leg is similar to side, 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 except for right triangles. We have another one called the leg, leg. If you have two legs, is that enough? Yes, because if you have two legs, you also have the hypotenuse. You get all three again. So that would be like this. But you know what else it can be? It could also be this one. Because if you have leg, leg, you've also got the angle in between, don't you? So this would be side, angle, side. That would be the same. There's two more. Hypotenuse, angle, and leg, angle. So if you have the hypotenuse and one angle, which one would this be like over here? It could be angle, angle, side. Yes. It could be angle, side, angle, because if you have this one, you automatically have this one because you already know this one, right? So the hypotenuse angle could be either one. How about leg angle? Say we have these two. Same idea. If you've got the leg and the angle, you've already got this angle because it's a right angle, so you've got angle, side angle. But if you have this angle, you also have this angle, so you have angle, angle, side. So this would be either one. But it does make it easier now because instead of having to get 3 sides congruent or 2 sides in an angle, all you have to do if they're right triangles already is get either the hypotenuse in the leg, hypotenuse in the angle, leg, leg, or leg angle. Just a little bit condensed. When you see the letters AA, what do you think of? Angle, angle, because you're in geometry class. But what if you were driving down the road and you saw an advertisement for AA meetings? Alcoholics Anonymous or Angles Anonymous? No, we're in geometry class, so this is going to be AA, which is angle, angle. But we know that we can't, there's how many angles in a triangle? Let's do this first. 3. So if you have 2 angles congruent, do you have all 3? Yes, because you know they have to add up to 180. We've already established this, but I just want to say it one more time. If you have 2 angles of one triangle congruent to 2 angles of another triangle, the triangles aren't necessarily congruent because you could have, here's a little triangle. There's a bigger triangle, and what if these angles are congruent and these obtuse angles are congruent? Would these 2 angles be congruent? Yes. Now, are the triangles congruent? We've got all 3 angles congruent to the other 3 angles. No, because the sides aren't the same length, correct? So how will we describe these 2 triangles then? If they're not congruent, what are they? Very good. They're similar. We haven't had this since one of the first lessons when we first talked about how we make the symbol for congruent. But similar means they're the same shape, but not the same measure or the same exact size. Are squares similar? All squares are similar because they all have 90-degree angles, but their sides, even though they're all the same size, they're not all identical to other squares. But all squares are similar. All equilateral triangles are similar. So why would we want to prove 2 triangles are similar? So we can find out the length. I'm going to give you an example. Let's pull up our old friend again. Let's say this is a 10, this is an 8, and this is a 6, and this is a right triangle. And then let's make one where this is 3, and this is a right triangle, and this is 5. What do you think this side's going to be right here?
4.
How do you know it's 4?
Because it has to be for the
Pythagorean theorem, we could figure it out, right? Because 3 squared plus 4 squared would be 5 squared, so that would be a 4. Now look at these 2 triangles. They are similar triangles, but if the triangles are similar, the sides have the same ratio. Remember ratio? I think we taught it in pre-algebra, where 1 is to 2 as 4 is to 8. Remember how you say that? 1 is to 2 as 4 is to 8, or you could do 1 is to 4 as 2 is to 8, right? And it's real important that you go in the same direction in the same order. So we could do a ratio here. We could say, here, you finish it for me. 4 is to 8 as 5 is to, what I did was I went 4 is to 8 as 5 is to 10, right? How about this one? 6 is to 3 as 8 is to 4. Now I started the big boy. 6 is to 3 as 8 is to 4. It's real important that you maintain the same sequencing, the same order, the same direction. So the first one I started and I went, you might say, long leg, of the small triangle to the long leg of the big triangle. And then because I went from the small triangle to the big triangle, then I'm going to go hypotenuse, small triangle, to the hypotenuse, big triangle. But this one I went reverse. I went short leg, big. Short leg, small. Long leg, big. Long leg, small. Get that? It's confusing. I'm even having to go slowly myself to get this. But you want to make sure that you go in the same direction. So you can describe these as mucho grande triangle versus itty bitty. This is not in the book. This is only for those of you that are watching the video, right? And you could say mucho grande hypotenuse to itty bitty hypotenuse. Or you could go itty bitty long leg to mucho grande long leg. But you got to make sure that you're moving from mucho to itty bitty or itty bitty to mucho. You've got to go in the same direction each time. That helpful? Okay. Let's see if we've got some hard problems here. Oh, we don't. These are all easy. Okay. The last thing, though, is that when we are doing proofs, we might come to something where we're going to use the angle postulate. And so when we have our statements and we have our reasons, one of the reasons could be angle postulate. Don't forget, if you have two angles, you really have three. But we can't do AAA, can we? Why is that? We'd be an automotive association. No, but we try to get it as condensed as possible. So if we have two, we know we have three. But if we have two angles congruent, we've got similar triangles. We've got ratios that follow. This lesson is called Transformational Geometry. That's not why we have a T up there. And normally what I do is I draw these on the Cartesian coordinate plane. But I had an inspiration in the morning, hopefully it was divine, and I drew my letters on clear, like real thin plexiglass, so that I could move them. Because transformational is we're moving things. So we're going to start with the letter T. Now you can, because it's a Cartesian coordinates, you could measure some points. You could say like the bottom of the T is over 3 and up 1. Or you could say the point where they intersect is over 3 and up 3. But I'm going to ask you, this one is called a translation. By the way, there's 4. There's translation, there's rotation, there's reflection, and there's dilation. And these appear in real life. So the translation is we're going to start at this point and we're going to move it over, so look at this right, over 6 and up 2, over to the right 6. So I'm going to move this over 1, 2, 3, 4, 5, 6, and then 1, 2. So this is what you have in your book. The T ends up there. Now you could again measure from the points, 1, 2, 3, 4, 5, 6, and then go up 2. You can measure from the bottom of the T's, whatever, okay? So if you wanted to make some out of clear, it really is pretty neat because then you can move them around yourself. So translations just move over and up, over and down, anywhere you want. But you describe them, same as we've done before, over 3, down 4, over to the left, -2, up 5, like that. That's a translation. The next one is a reflection. And so I have an R. And we'll untranslate our T. And we're going to put our R up here. And we're going to put the R starting, and I'm going to use this little point right down here. Looking here, over 2, up 1. Or you could look at the intersection point, over 3, up 2. But pick some points. What do you think reflection? A translation just moves the whole piece, right? What does a reflection do? What do you think? Yes?
It's like a mirror image?
Yeah, to reflect you have to have a mirror. But the key is where you put the mirror. Do you put the mirror here you put the mirror here? Do you put the mirror here? So the reflection is going to depend really on where the mirror is. So let's say that we were going to reflect R in this axis right here. The y-axis going up and down, we're going to reflect it, so it's going to look like this. So we could have just, we draw it, and then we reflect it in the axis, so it looks like this. See that? If we were just writing it and we didn't have the clear little plexiglass, we would say, well, we started 2 over here, so we go 2 over to that point, or we could say this point to the 3. But because it's reflected, it is inverted. It's not a translation would just go like this, but a reflection flips like this. Does that help? Okay? Boy, that's kind of a rough R. It looks like someone's been beating that one up. This next one, though, is a little bit tougher to get. And I think I'm going to put a little O in here just to make the distinction there, because this is called the rotation. Let me color in my rotation a little bit. And the rotation is going to start at the same place, but it's going to rotate counterclockwise. And if it went all the way around, how far would it go? How many degrees is all the way around? 360 degrees. So it depends, 2 things. How far you rotate it, and on what point do you rotate it. So the easiest is to do it, we're going to rotate it around the axis, the origin, where the 2 axes intersect. But you could rotate it around this point, you could rotate it around this point, and then it would go up here. You could rotate it around here, it would go way up here. So the point is critical, and how many degrees. So let's see if we can do this. This is the first time ever done on national television. I'm going to put my finger there. We're going to rotate this 180 degrees. Oh, if I may say so, that was good. Okay, so what we have now is, see, this point was up 1 over 2, and now we're down 1 over 2. This point up here was over 3, up 3. Over 3, up 3. See? So that would be a 180-degree rotation. If we kept going another 90 degrees, be something like that, and that would be a 270-degree rotation. If we kept going, so we had 360 degrees, we'd come right back to there. You see that? So what are the key points for rotation? Around which point and how many degrees, and you go clockwise or counterclockwise? Yes, counterclockwise, because that's what we've been doing for angles anyway, right? We start here at 0 and we go 90, 180. So we're doing the same direction, okay, as we've been doing. Now, I'm going to put up a problem up here, and I'm going to use my E, not because it's easy, but I'm going to put up 2 E's, and I want you to tell me how we moved these E's. And don't say with ease, because I already used that joke. So if we're moving the E's from there, and we're going to put this E up here, and that's, there you go. Okay, how could I get from here to here using either a translation or a rotation or a reflection or any combination thereof? And there's several ways, many ways. Just give me one back there in the back.
Rotation, 180 degrees.
Okay, a rotation. Where's my big R piece? Let's see if we can rotate that guy. Pretend that's an E. There we go. Here, we'll just make an E. We're flexible. Just got dead markers. Okay, so let's say that we were to rotate this, and that would be rotating all the way around. Okay, how many degrees do we rotate it? 180. Around which point? The origin. Okay, good. That's one way. Another way. Yes?
You mirrored it on both axes.
So I could mirror it. I could mirror it here, and then mirror it again. Very good. Can I do the other way? Could I start here and go to here and then go to here? Yeah. So I can do double. I can either do the x-axis and the y-axis or the y-axis and then the x-axis. Either one would work. Double reflection. Yes.
You can mirror it once, and then you can move it by
Translation.
translation.
Very good. So if I mirror it once, boom, then I could just slide it up. Okay, or I could mirror it, or I could translate it, and then I could mirror it. Very good. I think this is kind of cool myself. So there's different options for this, okay? So we've got translation, we've got rotation, we've got, what was the other one? Reflection. And there's one more, and I saved it at the end because it's going to make my nice Cartesian coordinates dirty. It's called the dilation. If I say dilate, what goes into your mind? What do you think about when I say dilate?
Eye doctor dilating your eyes.
Eye doctors messing with your eye. That's what I think of too. Have you ever done that? I mean, like look at a mirror, staring into the mirror, and then someone flashes on the light, and you see your pupils just go woo, or if they turn it off, it goes woo, because they really do dilate, don't they? This used to be very difficult to teach, but now that we have things called computers where we can drag the mouse and we can take a shape and we can stretch a square and that kind of thing, it's not so tough. But dilation looks like this. Let's say we're going to use the letter D just because we're dilating. And if I have this to start with, and I'm going to exaggerate a little bit to make it square. If I want to dilate this, what I would say is by a factor of 3. So I'm going to dilate it around the origin, so I want to make it 3 times as large. So this point here would be 1, and then it would become 3. This point would become, let's do this one, 1. Now it's going to be 3. This point would be here. This point would be here, here, here. Get the idea? So we're going to come over here. We're going to go down here. We're going to go over here. We're going to go up. Boy, how would I do that one? 1, 2. I head to this point over here. So I think it's going to be like this, right? Something like that? So each of the points, the whole thing dilates kind of, I don't know, it's not the right word. You ever heard of concentric circles? Circles that are all, well, it's going to dilate everything at the same point out. It's not going to all of a sudden go drop. It's every point is going to expand out or contract.
Like Russian nesting dolls?
Russian nesting dolls, perhaps, yes. Okay. Is that helpful? Transformational geometry. These last 2 lessons are about trigonometry. Now, we teach trigonometry formally in our book, which we call Pre-Calculus with Trigonometry. And we cover the whole basis of trigonometry. But oftentimes there's a few questions that will pop up on ACT or SAT questions that have to do with trig. So we thought we'd just drop these in here. It would be a good precursor to trigonometry later. But trigonometry, what do you think it means? Metry, measure, trig, triangle. It's measuring triangles. It's kind of like what we were doing a minute ago with similar too, because it is to do with ratios. You will often see, and people don't think of this, if you ever look at an old trig textbook, you'll see trig tables, and sometimes they use the word ratio, sometimes they aren't, or they don't, but these ratios are expressed. By the way, a ratio is the root for rational number. It's a fraction. But you and I know that we can do 1/2 is the same as 0.500, correct? Because trig tables are filled with decimal numbers. But decimal numbers are really ratios, trig ratios. There's 3 key ratios. They are the sine, the cosine, and the tangent. There's the abbreviations. There's the full spellings. You'll see these on scientific calculators. You'll see SIN, COS, TAN. They stand for these three. But they are ratios expressed usually as decimals. Okay? What would happen if you took a break from filming math videos and you went outside and you dropped a concrete block on your foot? You would have a broken toe. So how would you assuage the pain of your toe?
Pain medication?
Pain medication? What would you do first? Yes?
Lift the block.
Try to walk? Oh, lift the block off your foot. Okay, you lifted the block off your foot. You're in the house. You've been crying for a long time. Now, what are you going to do to ease the pain? Ice it or soak it, maybe? So I like to say you're going to soak a toa. You're going to soak your toa. Soak a toa. Now you have to remember that. Soak a toa. And here it is. So ka toa. Now let me explain where it comes from. If you have a right triangle, now in advanced trigonometry you can do this with any kind of triangle, but most of the time it's with right triangles that we start with, okay? And let's say that you have a 3, we use our old buddy, 3, 4, 5 right triangle, and we're going to put two angles in here. We're going to use theta and we're going to use alpha. How many different ratios or fractions can you make out of these three numbers right here? Give me one.
4 over 5.
You can do 4 over 5. Another one. 5 over 4. That's the next lesson. Let's just keep with the 4 and the 5 ones. 4 over 5. What's the other one? 3 over 4. What's the last one? 3 over 5. Those are ratios. Now, if I was standing at the point of theta right here, this is the opposite side. This is the adjacent side. This is right next to me. This is opposite me. And this is always the what? Hypotenuse. So opposite to right angles hypotenuse, this is the adjacent side. This is the opposite side. But what if I move? What if you close your eyes and I run up here and now I'm standing up here? What is the side opposite me now? 4 is opposite. This is adjacent. So opposite or adjacent depends on where you're starting. So if we're going to start right here, though, let's say we're going to start at theta. The sine is the opposite over the hypotenuse. Well, regardless of where you're standing, it's the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. I kind of got ahead of myself a little bit about where I'm standing because these ratios are the same no matter where you stand, but the numbers will change depending on where you stand. I'll illustrate that in a minute. Now, you see the T-O-A, TOA, C-A-H, CA, S-O-H, so, ka, toa. Because you want to remember those. You should be, when you think sine, you think opposite over hypotenuse. When you think cosine, adjacent over hypotenuse. You think tangent, opposite over adjacent. If you can think of a better way, let me know. I'll give you credit. Now, let's put some numbers in. If now I'm standing here at theta, what is the sine of theta? Sine of theta is what? Opposite over hypotenuse. So that would be 3 over 5, which I could write as a rational ratio fraction, or I could write it as 0.6000. Same thing. If you look in a trig table and you look under sine and 0.600, it will tell you what the measure of that angle is. Cosine. What's the cosine of theta? Still standing here. 4 over 5. How would I write that? 5 or 0.8. I put all these zeros because most trig tables I've seen have 4 decimal places. Okay, what's the tangent? Tangent of theta? 3 over 4, which would be what as a decimal? 0.7500. Is that okay? Do you also see, though, how these ratios would change if my position changed? If I was standing here at alpha, I've got to find a marker that can write. If I was here, what's the sine of alpha? Opposite is now 4 over 5, 4.8. What would the cosine of alpha be? 3 over 5. What would the tangent of alpha be? 4 over 3, which would be 1.33333, like that. Okay? So this is your trig ratios, they're called, the trigonometric ratios. Sine, cosine, tangent. You've got to know opposite, hypotenuse, and all that. But the key thing for finding the numerical value is making sure where you're standing, where you're starting. Are you starting here or are you starting here? Opposite. These are constant, but the numbers will change depending on where you're standing. And let's see if we've covered all the bases for that one. Let's do some, not just sine of alpha, let's do some real sines. If this is a 30, 60, 90 special right triangle, and this is the long leg because it's opposite the larger angle, what would be the length of this side here? 5. What would be the length of the hypotenuse? 10. Okay. What's the sine of 30 degrees, cosine of 30 degrees, tangent of 30 degrees? Now the sine would be what? Opposite. So OH, opposite over hypotenuse, so it would be 5 over 10, which would reduce to 1 over 2 or 0.5, right? It's either 1/2 or 0.5, same thing. What's the cosine of 30 degrees?
5 square root of 3.
Adjacent. Very good. So it would be 5 times the square root of 3 over 10. I could cancel that. That would be the square root of 3 over 2, which would be about, I think, 0.8660 or something like that. Comes to my mind because this is about 1.7 divided by 2. Okay? How about this one? Tangent of 30 degrees.
5 over.
Opposite over adjacent. 5 over 5 square root of 3. These cancel. You're left with 1 over the square root of 3. Uh-oh, the radical police are coming. So we multiply times the square root of 3 over 3. We get square root of 3 over 3. Which 1.7 divided by 3, I think this is 0.5771. Don't trust me on that, but it's close. Now let's go back and do it from 60 degrees. Sine of 60 degrees would be what? It would be, this would now be the opposite over the hypotenuse. 5 square root of 3 over 10. Hey, we just did that one, didn't we? Yeah, so we're going to say 0.8660. Okay, what would be the cosine of 60?
5 over 10.
Standing here, 5 over 10, very good, which is 0.5. We did that one up here. How about the tangent of 60?
5 square root of 3
Over 5, which would be 5 square root of 3 over 5. 5's cancel, it would just be the square root of 3, which is something like 1 point, what did I say? 1.7, something like that? Okay, let's say 1.7, blah, 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 blah. But it does have a value, but they take it usually to 4 decimal places. So there you go. This help you? So if you run across this on a test, just remember SOHCAHTOA, look at the ratios, and you'll be in good shape. Now that we've learned the trig functions, sine, cosine, tangent, and let's go back to our original 3, 4, 5, and make sure I did alpha and theta. You remember when I asked what are the possible ratios, and we said 4 over 5, 3 over 5, 3 over 4, but somebody said 5 over 4. And it turns out that there are 3 more ratios in the different directions. And these are called inverses. So if the sine is the opposite over the hypotenuse, the cosecant, abbreviated CSC, is the hypotenuse over the opposite. So for the sine of theta, it would be 3 over 5. But the cosecant of theta would be 5 over 3. Get that? And I don't know how to make this one. Cho, so far. You can make up your own story. I can't make up any SOHCAHTOAs. I don't know how to do it for this one. So that's your assignment for tonight. If we have the cosine is the what? So, ka. What do you think the secant is? It's the hypotenuse over the adjacent. Or you could say 1 over this, which when you've done all your finagling with fractions comes out to the same thing. Okay, then you have the tangent and the cotangent. If the tangent is the opposite over the adjacent, the cotangent is the adjacent over the opposite. That's all. So this lesson is just introducing these. Now, how do you keep these straight? Because it is interesting that you have sine, cosine. You have secant, cosecant. Now, how did I keep those straight? I just think of, well, if this starts with an S, this is the opposite. This starts with a C, this is the S. But these are kind of like co-functions of each other. If you noticed before that the sine of 30 and the cosine of 60 were the same because they're co-functions. And you've got tangent, cotangent. But these are sine, cosine, secant, cosecant, tangent, cotangent, and whatever you want, whatever memory devices you can create in your fertile minds, go for it. And there's one more trigonometric, which we call an identity, which you could figure out from what you know of trig so far. I'm going to replace these numbers with the letters again, opposite, adjacent, hypotenuse. And I'm going to start off by saying Pythagorean theorem, which would be what using these letters? Very good. Isn't that correct? Okay, so we have the opposite squared, leg squared plus leg squared, a squared equals hypotenuse squared. If I was to divide through all the way by h squared, this would become 1. That's an a, correct? What do we know about squares? Well, if it's o squared over h squared, that's the same as o over h squared plus a over h, the whole thing, squared equals 1. Do you know any ratios? What do you know is the same as the opposite over the hypotenuse? Remember? SOHCAHTOA. The sine is opposite over hypotenuse. The cosine is adjacent over hypotenuse. Remember that? So in everywhere I've got an OH, I can replace that and put the sine. If I have a over h, I can replace that ratio and put the cosine. And so what you have is the sine squared plus the cosine squared equals 1. Or the sine squared of theta plus the cosine squared of theta equals 1. Isn't that pretty cool? But it's based on what you know about trigonometric ratios and Pythagorean theorem. But you might run across this on a test where they'll say something like this. What's 1 plus sine squared plus cosine squared? What's the answer? 2. Because, very good, because sine squared and cosine squared adds up to 1, so 1 plus 1 is 2. Or they might have sine squared plus cosine squared minus 1. What's that equal to? 0. See, you're whiz kids already. Or they might have 1 minus the cosine squared equals what? All you do is you subtract cosine squared. This is equal to the sine squared, right?